Example 13-5, elevation effect on atmospheric pressure. Question number 1A, determine the variation in pressure in the Earth's atmosphere as a function of height y above sea level, assuming G is constant and that the density of the air is proportional to the pressure. This last assumption is not terribly accurate, in part because temperature and other weather effects are important. B, what elevation is the air pressure equal to half the pressure at sea level? So we have to find the relationship in the pressure and the density first. So usually the pressure is proportional to the density and density proportional to the pressure. The ratio between the density at different altitude, different height above the sea level is also proportional to the ratio between the pressures at those two different heights. So usually the density of the gas, which is air in this problem, is proportional to the pressure. So from that, the ratio between, as I said, the density of gas at different level due to the the pressure applied to the gas at different height should be proportional to the pressure ratio of the pressure at different height. So here P naught is atmospheric pressure, which is 1.013 times 10 to the 5 Newton square meter. And the density at sea level should be 1.29 kilogram per cubic meter. So this is the density of the air at sea level. First of all, we know that the pressure, fractional pressure, is a function of the height, which is minus density times the acceleration, gravitational acceleration constant G. So now if you replace density of gas at height at the height above sea level, then that should be P times rho naught over P naught times G. So if you change, if you swap the P and Y from both sides of this equation, then that should be dP over P equals minus rho naught over P naught G dy. So as you can see, this equation is basically given by the integral of the pressure and the height from the sea level all the way to the given height of this problem. So if you integrate it, then left-hand side, let me just write it up, the whole equation with the integral. So that is integral of Tp over P from P naught to the P equals minus rho naught over P naught, which are the constant value, times G over integral times the integral of dy height from 0 to the specific height of interest. So we need to actually drive formula out of this integral. Then that should be like an integral of 1 of P in dP should be log function. So that is log P from P naught to the P. So that is log, natural log P minus natural log P naught, which is log P over P naught, is minus low over P low naught over P naught times G Y. So now we want to actually express this equation in terms of the density and the pressure at sea level. So pressure P, which is a function of Y, is P naught times exponential function minus low naught Z over P naught times Y. So as you can see, that pressure is exponentially decay in height Y. So Y goes higher than pressure of the air is just getting lower. So number B, we gotta plug the numbers of condition into this formula. So let's take a look at this coefficient just before variable Y. So that is low naught over P naught times G, right? So that's low naught from that is 1.29 kilogram per cubic meter. So let me just plug it. It's 1.29 kilogram per cubic meter times G is 9.8 meter per square second. And the P naught is 1.013 times 10 to the 5 Newton square meter. So if you plug that all the numbers into the formula, then that should be 1.25 10 to the minus 4 inverse meter. So now the condition is at what elevation is air pressure equal to half of the pressure at sea level. So the pressure itself, the P, becomes half of the pressure at the sea level. So that should be 1 of 2. P should be 1 of 2 P naught. So you plug that, then that should be 1 of 2 P naught equals P naught exponential minus low naught G over P naught times Y. So if you cancel P naught out of both sides of the equation, then that should be 1 of 2 equals exponential function 1 minus 1.25 10 to the minus 4 inverse meter times Y. So now we want to actually find Y out of this formula. From that, Y should be log exponential log 2 over 1.25 times 10 to the minus 4 inverse meter. So that is 5,550 meter. So when you reach the height of the 5,550 meter, that pressure becomes half of the pressure at the sea level.